Talk about the biological effects of radiation, section 20.6. Well, we all know that radiation is not good for us, depending on the amount and how quickly we are exposed to it. If we are exposed to a radiation source for a long time, it could actually it causes damage, but it could even cause cancer. What can happen as radiation hits our cells, it will cause some damage. Now, it depends on where that damage occurs. If it happens to damage our DNA, then it alters that cell. Obviously, the DNA is what codes for everything in our cell, and so it will cause damage to that particular cell, and it could turn it into a cancer cell, and it starts to multiply, and it gives us a tumor. That is a direct effect of radiation. Now it can ultimately, that's what cancer is, but it can just cause extensive damage. Depending on where it hits the cell, it can cause extensive damage. Now we have to understand that we are exposed to radiation on a daily basis because there are naturally occurring isotopes. For example, every time we eat a banana, we are being exposed to an isotope, a radioactive isotope of potassium. However, those are so small, doses are so small that it doesn't really affect us much. Every time we eat plants, we are taking in carbon-14 as well as the regular form of carbon-12. And so we are exposed to radiation due to naturally occurring isotopes. We don't have to face a sample of uranium to get radiation from that. We are getting some on a daily basis just due to naturally occurring isotopes. The difference is that the dose is very small compared to heavy element radiation source. Now let's talk about shields. These shields are materials that will stop radiation. If I'm talking about the alpha particle, this is the heaviest sort of particle that is emitted from a nucleus. And because it's heavy, it doesn't travel as fast or as far. It can be stopped by a shield, a simple shield such as just a piece of paper. And therefore, the alpha particles are the easiest to stop, the easiest to protect from. If we're talking about beta particles, those particles will penetrate paper. They'll penetrate our hand or our flesh. They will be stopped, though, by a piece of metal. So beta particles they can penetrate our skin, but they can be stopped by a piece of metal. So if I put a piece of metal in front of a source of beta particle, that means that it will stop them, so my hand or my body will not absorb that radiation. If I have neutrons, those will penetrate all three, so that if the nucleus is emitting neutrons, it will penetrate the paper and the body and a piece of metal. It can be stopped by water. So in the nuclear reactors where you do have a lot of neutrons given off, you know that there's a lot of water that absorbs that energy, and that's because it can stop neutrons. Gamma rays, which are the lightest, they really have no mass and no charge. They can penetrate through all of the previous shields that I talked about, so paper, a body, a metal, water, even large chunks of concrete. They are stopped with very large chunks of lead. And so every time when we talk about nuclear decay reactions, in a nuclear reactor, for example, they have to have a lot of these shields to protect people who are working there. And if we're wanting to store the nuclear waste from these reactions, we have to have We can't just put concrete, we have to line it with lead to be able to stop the gamma radiation from leaking out. And these are the important, so learn how each of these particular particles can be stopped by these shields and by what type of shields. So gamma, neutron, and beta and alpha particles, they can be stopped, but they just differ in the shield that is most useful to stopping them. Note that the alpha particles are not as damaging to us as the other different types of radiation, the gamma being the worst because it penetrates the farthest and it's very high energy, very, very high energy, and so it causes the largest damage to our bodies than all the other types of particles. Now, these are the three ways that we measure radiation. We can talk about the activity or the amount of radiation absorbed or the equivalent dosage. Remember these three measurements of radiation. The activity is measured in Curie or Becquerel. Becquerel is the smaller unit. Curie is 3.7 times 10 to the 10th becquerel, so much larger unit. This is a measure of how much radiation is given off per unit time. So 1 becquerel is 1 disintegration per second. 1 Curie is 3.7 times 10 to the 10th disintegrations per second, or decays per second. This is a measure of how much radiation is being given off by my radioactive source. This measures the activity of my radioactive source. But I may not be interested in just the activity or the radiation that is being released by my source. I might want to look at the radiation that is absorbed. That is expressed in rads and grays. 1 gray is equal to 100 rads. Learn these relationships. This is a measurement of radiation that is absorbed by tissue. So how much radiation is absorbed by tissue? This told me how much radiation was being given off by the source, the radioactive source. This tells me how much of that radiation is being absorbed by tissue, because not all of it is being absorbed by the tissue. Gray is then defined as joules of energy, so how much energy is absorbed by 1 kilogram of body tissue. These two are mostly used in the health industry by doctors and nurses. This is how I know how much radiation is being absorbed out of that original amount of radiation that was given off. And then the last measurement of radiation we're going to talk about is the equivalent dosage. How much, it's expressed in rem and sievert. This is the SI unit, the sievert. This actually measures the damage that is caused by radioactive exposure. This measures the activity or the radiation that is released by the source, the radioactive source. This measures how much of that radiation is absorbed by the tissue, the body, and this measures out of this absorbed radiation how much damage is it caused, because not all of the radiation that's absorbed is going to cause damage. So you have three tiers or three levels. This measures the total radioactivity that is given off by the source. This measures how much is absorbed by tissue, and the dosage, the equivalent dosage, measures how much damage is caused by the absorbed radioactivity in tissue. And 1 sievert, this is the relationship, 1 sievert is equal to 100 rem. The average person receives about 360 millirems annually just by living. We said we're exposed to naturally decaying isotopes because they occur naturally in our food that we eat, etc., etc. So we are recipients of about 360 millirem of exposure damage just from being alive. However, our bodies are made so that we can get rid of, or we can manage that little bit of damage. When we get to larger amounts, however, our body cannot keep up with it. And especially, so it depends on how the dose, the initial dose of radiation that is released and absorbed, that will the damage then will depend on these two, but it will also depend on how quickly. So I could be exposed to an amount of radiation that can add up to being kind of a large amount, but because it's spread over time, it doesn't really affect me as much as a smaller dose of radiation that is given very quickly in a second or so. That can really cause a lot of damage. So it can depend on the dosage, but it can depend on the time of the exposure of the body to radiation. But always remember that there is a little bit of radiation that we're exposed to just from being alive and consuming foods that have naturally occurring isotopes in them, like the banana that I mentioned that has potassium, and some of that potassium is a naturally occurring isotope of potassium, or carbon that is found in plants. Some of the carbon that makes up the plants is carbon-14, which is a naturally occurring isotope of carbon, versus carbon-12, which is the most stable. This concludes the lecture for chapter 20. Please read over the text, listen to the lecture, watch the problem videos, and don't hesitate to ask me for any questions that you might have.